All right, let's just jump right in. Have you ever really stopped to think about how your computer does, well, everything at once? You're streaming music, you've got a dozen tabs open, a huge file is downloading, and it just works. It doesn't crash. It feels like magic, right? But it's not. It's actually this incredible high-speed ballet of coordination. So today, we're going to pull back that curtain and see how computers manage this amazing symphony of tasks. But to really get our heads around this, let's start with a question that's a bit more human. You can just forget about computers for a minute. Think about any high-performing team. How do they build something complex and do it fast without it all just turning into a total mess? It's really the fundamental problem of working together on anything important. And you know, there is no better place to see high-stakes teamwork under pressure than a professional kitchen during the dinner rush. I mean, it is the definition of controlled chaos. You've got all these different chefs, all working on their own things, but somehow these perfect dishes just appear right on time. This kitchen, this is going to be our guide for understanding what's happening inside a computer. So let's make that jump. From the heat of the kitchen to the logic of computer code. What we're really talking about here is the language of parallelism. It's the science of doing many things at once. And you'll see, just like in that kitchen, success comes down to one thing: how all the different chefs, or in our case, tasks, talk to each other. Now, here's the official fancy term for it: inter-task interaction. It's really just a formal way of describing all those tiny little conversations and handoffs and moments of teamwork that happen inside your computer millions of times a second. Honestly, it's the secret sauce of all modern computing. But let's forget the jargon for a second. This right here, this gets to the absolute heart of it. It's the chatter. It's the handoffs. It's the shared timing. This is what separates a bunch of individuals just cooking in the same room from a real professional culinary team. And it's exactly what separates a slow, clunky program from one that's lightning fast. Okay, so let's break this down a bit more. The very first piece of this puzzle is just understanding the flow of data. So back in our kitchen, this is the flow of ingredients. You know, how does the sauce get from the sauce station all the way over to the grill? This question is absolutely critical. And this image, well, it captures a core concept perfectly. It's called data dependency. It's a simple rule. Task B cannot finish until it gets something from task A. The grill chef is literally stuck. He's just waiting on that sauce. Inside a computer, it's the same deal. One part of a calculation is just sitting there, waiting for a result from another part. It is a fundamental link in the chain. So, if a handoff has to happen, the next question is about size. Is the sauce chef handing over just a tiny little spoonful for a garnish, or is he handing over a full liter of sauce? This is what we call communication volume. The sheer amount of data, or sauce, being passed around totally changes the interaction and how long it's going to take. And all of that waiting time? It's got a name. It's called communication latency. And let me tell you, this is the #1 killer of performance. It is just dead time. It's the time the grill chef is standing there, totally unable to work. The longer that latency, the bigger the bottleneck for the entire kitchen. Reducing this wait time is one of the single biggest goals in designing fast computer systems. And building on that, you have to realize that not all these interactions are created equal. A one-way interaction is simple, right? The sauce chef hands over the sauce. Boom, done. But a two-way interaction, well, that's a conversation. The grill chef yells over to the veggie chef, "Hey, how long on those asparagus?" And now he has to wait for a reply. That little request and response cycle takes way more coordination. Okay, so we've talked about the flow of data. Now let's get into the rules that actually govern that flow. This isn't about what's being passed around anymore. It's about how and when. These are the kitchen's and the computer's rules of engagement. So first up is interaction frequency. Just think about it for a second. Are the chefs constantly yelling back and forth, coordinating every single slice, every single stir? Or do they just get their main orders at the beginning and then work pretty much on their own until the very end? High-frequency communication can be really necessary, but it also creates a ton of noise and overhead. And all of this leads to what is probably the most dramatic moment in the kitchen: synchronization. This is that critical point where everyone has to stop what they're doing and wait for each other. The steak, the veggies, the sauce, they all have to land on that plate at the exact same time. In computing, we actually call this a barrier, a point where no single task can move forward until every other task has reached that same exact spot. It's essential, for sure, but man, it can also bring the whole operation to a screeching halt. And finally, Let's zoom out and look at the whole pattern. A structured interaction? That's like an assembly line. It's totally predictable. Every single dish is made the same way, the handoffs are simple, they're all planned out. But an irregular pattern? That's the chaos of a la carte service. Every order is different, and it demands constant, complex communication just to figure out what to do next. Different problems that we ask computers to solve fall into one of these two camps. Okay, so we have spent a lot of time in this kitchen. Let's bring it all back home to the computer and talk about why any of this really actually matters.
So here's the bottom line. This isn't just a fun analogy about cooking. Understanding the dynamics of that kitchen gives us this incredibly powerful way to think about designing more efficient computers. Every single characteristic we just talked about, from data dependency to the interaction patterns, is like a knob that programmers and engineers can turn to make software run faster and smarter. And when we get these kitchen dynamics right in our code, well, the results are amazing. We cut down on overhead, which means less time is wasted just talking, and more time is spent doing actual work. We improve efficiency, which means faster performance. And that translates directly into things you and I use every single day. Smoother video games, way more accurate weather forecasts, and much more powerful AI. Which really leaves us with a fascinating final thought to chew on. For decades, we have tried to make computing as predictable and orderly as an assembly line. But as the problems we're asking computers to solve get more and more complex, things like modeling the human brain or climate change, are we going to need to design systems that actually thrive in chaos? Systems that work less like a rigid assembly line and more like a team of creative chefs, all improvising together in one brilliantly coordinated kitchen. It's definitely something to think about.